Welcome to Ask and Learn.
Hey guys, let's do problem 43. In this problem it says where in the column is the greatest risk of contamination. The first problem is that now liquid entrainment is the amount of liquid which is trapped on the upper section of the safe plate. In distillation column, entrainment occurred due to the high velocity of vapor flow rate which disturbed the transfer of mass. Given the temperature of the column at the bottom is 100 degrees Celsius, which is higher than the top. And therefore the vapor velocity at the bottom of the column will be high. Therefore, bottom of the column is at the greatest risk of entrainment. Next, we need to calculate the minimum column diameter. Let's do that. It is given that the vapor flow rate is 25 pound mole per minute. Let's convert it to mole per second. Which gives us 189 mole per second. Now the volumetric flow rate of vapor can be calculated using the ideal gas law. let's insert all the values. These are known values. The molar flow rate is 189 mole per second. Gas constant is 0.0821. Liter atmospheric pressure, mole inverse 1, Kelvin inverse 1. The temperature given here is 100 degrees Celsius. Let's convert it to Kelvin. The pressure is 1 atm. Therefore, the volumetric flow rate is 5784.88 liter per second. Now we need to convert it to feet cube per second. Let's do that. From here we get the volumetric flow rate is 204.06 feet cube per second. Now we know that area is equal to the relation between the area and velocity and vapor flow rate. We can use that. We know that area is equal to the vapor flow rate divided by velocity of vapor. Also we know that area is equal to pi r square or pi d by 2 square. From here we get diameter square is equal to 4 multiplied by area divided by pi. We can use these two relationships. D square is equal to 4 by pi multiplied by these two relations. Now we can use the velocity is given as excuse me, the velocity is given as 5 feet per second, and once we do this calculation we will get that the diameter, the minimum column diameter is 7.21 feet. Okay, then next we need to calculate the velocity of vapor at the bottom of the column. Problem C. The column is constructed with a diameter of 10% greater than the calculated part, greater than what we calculated in part B. In this case, the column in problem C is constructed with a diameter 10% greater than that calculated in problem B. Therefore, the new diameter of the column is 7.21 feet plus 7.21 multiplied by the 10%. Therefore, it is 7.931 feet. Then the new diameter is 7.931 feet. Then we can calculate the area of the column. which is 49.38 feet square. Therefore, the velocity of the vapor at the bottom, the velocity of the vapor at the bottom is the velocity is 4.13 feet per second. The velocity of vapor at the bottom of the column is 4.13 feet per second. The next question is, we need to calculate the velocity of vapor at the top of the column. Let's do that. We know that the volumetric flow rate of vapor is V is equal to nRT divided by P. All these values are given. The total molar flow rate is 189 mole per second. Gas constant is 0.0821. Liter atm, Kelvin inverse 1, mole inverse 1. Temperature given here is 65 degrees Celsius. Let's convert it to Kelvin scale. The pressure is 1 atm. Therefore, we get the volumetric flow rate of vapor is 5242.15 liter per second. Let's convert it to feet cube, liter to feet cube. Therefore, we get the volumetric flow rate of vapor is 185 feet cube per second. Then velocity at the top, feet cube per second divided by the area, which is 49.38 feet cube. Then we get the velocity of vapor at the top of the column is 3.74 feet per second. Feet per second. The next problem says, what would be the new pressure? Let's try to find it out. We know, according to the ideal gas equation, pressure is directly proportional to the moles or the molar flow rate. Therefore, pressure is directly proportional to the number of moles, or we can say that the molar flow rate. It means that if moles or molar flow rate increases, then the pressure of the column also increases. Therefore, if the vapor molar flow rate doubled, the new pressure of the column would be doubled.